When you work with modern search systems and retrieval applications, the size of your data structures becomes a critical bottleneck. You are dealing with vector embeddings, which are essentially long lists of numbers that represent the meaning of text. These vectors allow machines to understand similarity, but they come with a heavy cost. Storing millions of these vectors requires significant memory, and calculating distances between them consumes substantial processing power. To make systems faster and cheaper, engineers often look for ways to shrink these vectors without losing the quality of the search results. This is where the concept of compression enters the conversation. There is a specific technique known as Matryoshka embeddings that solves this problem elegantly. The name comes from the Russian nesting dolls, where smaller dolls fit inside larger ones. In this context, a Matryoshka embedding contains all the information needed for a smaller dimension inside the larger dimension. You can simply cut off the end of the vector, and the remaining part still holds the most important semantic information. This allows for flexible compression where you can adjust the size of the vector on demand based on your hardware constraints. However, not all models possess this natural property. Many powerful models, including the BGE M3 system, do not inherently guarantee that the first dimensions contain the most critical information. If you try to truncate these vectors naively, you are essentially throwing away the most valuable parts of the signal. You are cutting off the signal where the data is dense and keeping the noise where the data is sparse. This leads to a significant drop in retrieval performance. The system starts missing relevant results because the vector no longer accurately represents the original meaning of the text. To solve this without retraining the entire model, engineers have turned to a statistical technique called principal component analysis. This is often abbreviated as PCA. PCA is a method used to analyze data and identify patterns. It works by finding the directions in which the data varies the most. Imagine you have a cloud of data points in a three-dimensional space. PCA finds the axes that capture the maximum variance in that cloud. By rotating the data so that the most important information lies along the first few axes, you can project the data onto a lower dimensional space. When you apply this rotation before truncation, you are fundamentally changing the geometry of the embedding space. You are aligning the information density with the dimensions that you intend to keep. Instead of blindly cutting off the end of the vector, you are ensuring that the beginning of the vector contains the bulk of the information. This hybrid approach bridges the gap between Matryoshka and non-Matryoshka models. It allows you to take a legacy model or a model that was not designed for compression and make it behave as if it were. The results of applying this technique are substantial. When you apply PCA before truncation, the retrieval performance of non-Matryoshka embeddings improves significantly. It effectively narrows the gap with specialized Matryoshka models. The standard practice of simple truncation discards critical variance, but PCA optimally rotates the embedding space to preserve information in the leading dimensions. This means that even if a model was not trained to be Matryoshka, you can achieve similar multi-granularity flexibility through this pre-processing step. This has profound implications for engineering pipelines. You do not necessarily need to train specialized Matryoshka architectures to achieve efficient variable length compression. The technique enables on-the-fly compression of legacy, or non-Matryoshka models, making them immediately compatible with resource-constrained environments without retraining. This is a game changer for organizations that rely on older models or have limited compute resources for retraining large language models. However, there is always a trade-off in engineering. You must consider the latency and throughput costs associated with this approach. Applying PCA requires a matrix multiplication step before the truncation occurs. This adds a small computational overhead to the inference pipeline. In some cases, the cost of the PCA projection might slightly increase the latency of the initial query processing. But when you weigh this against the benefits of reduced storage and faster distance calculations in the retrieval phase, the balance usually tips in favor of compression. The throughput gains from processing smaller vectors often outweigh the initial projection cost, especially when dealing with massive datasets. Furthermore, the decision to use this method depends on your specific use case. If you are running a high-frequency search engine where every millisecond counts, the overhead of the projection might be a factor you need to tune carefully. You might choose to pre-compute the PCA-transformed vectors during the indexing phase, rather than doing it at query time. This shifts the computational load to the offline pipeline, ensuring that the online search remains as fast as possible. This flexibility allows you to optimize for either storage savings or query speed depending on your infrastructure. The broader picture suggests that future embedding pipelines may not require training specialized Matryoshka architectures to achieve efficient, variable-length compression. We are seeing a shift where the architecture of the model is less important than the pre-processing applied to it. This decouples the compression strategy from the training strategy. It means that a model trained for general-purpose tasks can still be optimized for specific deployment constraints through mathematical transformation rather than architectural changes. This approach also opens up new possibilities for hybrid systems. You could run a high-dimensional model for complex queries and a lower-dimensional version for simple queries, all within the same infrastructure. The system could dynamically choose the dimensionality based on the complexity of the user request. This dynamic scaling is only possible if the compression method preserves the semantic quality of the embedding. PCA provides that preservation, making it a robust tool for adaptive retrieval systems. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.